Thank you to everybody for inviting me, for being present. I have to confess that this is an ill-prepared lecture, not out of negligence, but out of personal circumstance. But I hope that nevertheless you're going to find it interesting. I'm going to talk about colloidal liquid crystals because nanocolloidal liquid crystals are currently a subject of much interest. I'll try down the road to explain why in engineering people think that these things are interesting things to look at. They're also interesting from from the point of view at least of mathematicians, theoretical physicists and chemists. And again, I'll try and show what they're interested in. And towards the end, if I get there, I'm going to show you all the problems that I can't do. And if you turns out that you can do them, I'll shoot you. Whoops. Right. But probably I will discover the solutions on some Chinese website tomorrow morning. Okay. Roughly speaking, that's what I'm going to talk about. The particular kind of colloidal liquid crystals that I have been concerned about are, well, we call them magnetic and electric. That's because they consist of colloidal particles. I'll tell you a little bit about that. And the colloidal particles themselves are either ferroelectric or ferromagnetic, and they're sitting in a liquid crystal background. So let's just show you some. Okay, just so that you know, in case you didn't, what a liquid sample of liquid crystal looks like. Actually, I am the experimentalist. It's the only experiment I ever did in my life. And there's my Bunsen burner on the left, and you can see that they are transparent in the isotropic phase, and they are turbid, sort of whitish, a bit like white paint in the nematic phase. And that's why we talk about the clearing point. And the colors are because the system in question is slightly cholesteric, and so these are selective Bragg reflections, right? But these are the kind of pictures that were seen by the original experimentalists. Here are some lyotropic liquid crystals which seemed to have simply escaped from another presentation. Okay. All right, so actually one of the interesting questions is not so much, is simply what do we mean by understanding what kind of approaches does one want to use in order to try and understand what's going on. And there's a whole variety of different kinds of approaches, and I'm going to be slightly, shall we say, opportunistic, right? So the old-fashioned way of doing ordered phases was to use what some people call a molecular field theory and some people call a mean field theory, which says, I know what kind of order parameter I'm looking for, so I know roughly, I'm going to pretend I have a mean ordering field. It doesn't matter whether it's a liquid crystal or a magnet or something. I'm going to pretend that I have an ordering field that has the same symmetry and is proportional to the amount of order that I have already, and then I have a factor of proportionality, and then somehow or other I'll get a feedback, and if I am lucky, I will actually get an ordered phase. And this is what Curie and Weiss did in 1905, I guess. And of course, they had no idea what was causing magnetism. They just said, let's suppose that it's like this. And it took a long time before people figured it out. And so we sort of work up in degrees of complication. The density functional theory is a sort of more complicated version of this, in which we try and look at the interactions build in the interactions between the particles in a cleverer way. There are various different flavors of computer simulation, which those of you who have been here longer will be familiar with, but it, roughly speaking, consists of how much detail of what's going on do I actually put into my simulation. And of course, depending on what question I am asking, the amount of detail is important. And then again, I may simply have a mathematical problem concerned with some configuration at a much longer length scale, and that's elastostatics or hydrodynamics. So those are the kind of things that I'm going to be looking at. Here's a picture of twist, bend, and splay, and those are the three key macroscopic parameters. And I'm going to screw this up, aren't I? Which button do I, is this the button that I press? It's an experiment. No. Oh, there we are, right. And here's a term that tells us that the liquid crystal, right, so this is the energy. I haven't shown a dissipation function, but here's a susceptibility, again, something that if I'm doing macroscopic work, I simply take as given, and then I can scale with respect to something like this. And here is an electric field. Okay, so right. So now, what I just want to give you a little bit about colloids, because colloids and liquid crystals are both complex, sort of complex modes of matter, forms of matter. They are not simply earth, air, wind or fire, as it were. They're something more complicated than that. They both were discovered in the late 19th century, and of course, when you look at them, right, they look. If you take a macroscopic sample, they look remarkably similar to each other. And I think I have a picture. There I have a picture. Okay, so colloidal suspensions are, of course, very common in the real world, right? All sorts of things that you eat or drink, milk, mayonnaise. Most of us don't drink or eat mud, but you can never tell. There must be some enthusiasts, some animals that are keen on these things. And motor oil, paint, and toothpaste are also not foods, but again, for their activity, they require having something that is larger sitting in something that is smaller. Right, fluids inside living organisms. There are some technical terms, emulsions, which are liquids, liquid droplets stuck inside other liquids. Aerosols is when it's in gases. The typical size is something between, whoops, mustn't fall off, nanometers and microns, right? Right, what I want are large particles with respect to the underlying matrix, in other words, with respect to the microscopic particles, but I don't want them so large that they are all going to fall to the bottom of my sample. And of course, you know, if you take some mayonnaise, actually, and you leave it around for long enough, it'll layer. And that's because, roughly speaking, and if things are too heavy, then there's a density proportionality, which is roughly, let's see, right. So, right, if I'm in a column here, and here is L, then rho of H equals e to the minus mgh over kBt, right? So, right, m, of course, is not actually the mass, it's some kind of effective mass, because we're all aware that balloons go up rather than down, but that's only because of Archimedes' principle, right? So I'm looking at the effective mass, I'm looking at the mass displaced, and of course, if on the scale of my sample, my rho changes very greatly, then I have to sort of think of myself as in an inhomogeneous medium, whereas as far as a nitrogen atom in this room is concerned, of course, it doesn't make any difference at all. And if, of course, the density changes on the length scale of the particle itself, then for all intents and purposes, we may suppose that the particle falls to the bottom. And of course, that's what we're aware of if you drop a metal ball into a large glass of water, it will simply drop to the bottom. Okay, so there's a whole load of these things, and as I said, sometimes in thermodynamic equilibrium, sometimes not. And from the point of view of liquid crystal technology, the idea is you put a little bit of these things into your liquid crystal, and you only have to put very small amounts, proportions of certainly of maybe even as low as 1 part in 10 to the 4 by volume, certainly 1 part in 10 to the 3, and the properties might change dramatically. And the idea is, if you are a chemist, If you're a chemist, you're sitting there very carefully and you're making some new compound, and there are just discrete compounds that are available, right? And you may not be able to quite, right? So you like to mix things, of course, and if you mix things, then you'll get some advantages of both kinds of particle. But the hope somehow is that I pour some of my nanoparticles in there, and lo and behold, my properties will change in a desirable way. And that's what happens if you go over to engineering. They will show you some mixture, and they will do engineering here, to which I commend, incidentally. I commend a visit to the engineering department. There are two competing liquid crystal groups there. Okay, so here is a picture. There on the left we have some milk, and there on the right we have some liquid crystal, and you can see that they sort of look the same. And the reason they sort of, well, on the left, of course, there are small particles of fat that are sitting in the water, and the small particles of fat are scattering the light. So that tells one thing. We actually have to, if we actually want to explain the experiments, we have to understand what the light scattering is doing, which is something that we often forget. And on the left-hand side, we've got, well, it turns out we've got orientational fluctuations. Here we have density fluctuations. Here we have orientational fluctuations, and big fusses over 100 years ago about whether or not this was the same thing. Okay, so, all right. So here are a variety of liquid crystal colloids, right? They could be rod-like colloidal particles suspended in an isotropic medium, which order in a liquid crystalline fashion. The rod-like particles could indeed be viruses, which was the original sort of the canonical case, which led Onsager to think about these things in the first place, right? They could be, on the other hand, suspensions of particles in a liquid crystalline medium. So you could be putting spheres or round-ish kind of things in your liquid crystal, and that would be affecting the nature of your liquid crystalline order, right? Or they could be, and this was the original example over 100 years ago, they could be droplets of a liquid crystal medium suspended in another medium, and the typical signature of these things is that they aren't spherical, whereas droplets, liquid droplets, they should be spherical, and if they're not spherical, something funny must be going on, and the something funny is to do with the balance between anchoring energy on the one hand and elastic energy on the other. And here's a picture, right? Here's a picture of a liquid crystal colloid with some spherical particles and some liquid crystalline particles. Those are the blue ones, and you can see that the liquid crystal particles are having trouble because they're having to turn, and this is costing us free energy. And the fact that it's costing free energy means that maybe, just maybe, the system doesn't like it. It certainly doesn't like it, using the anthropomorphisms that obviously there are no human feelings involved. But anyway, from the point of view of Helmholtz free energy, it's higher than it would have been if the system were isotropic, and the result is that a system like that is less likely. And so it's right. So as a general rule, solutions of colloidal particles in liquid crystals are harder, and things come out of solution at lower. Okay, here's a picture, actually. We were trying to do some experiments. Well, of course, not me personally, because things break if I go into the lab. But anyway, some friends, and actually we were hoping to see our magnetic particles sort of all nicely distributed through the system, and instead of being nicely distributed through the system, right, they took a picture with an electron microscope, and here's a certain amount of aggregation, and you can see that in this bit it's aggregated, and over there it isn't, so there are some density fluctuations. And this is the kind of thing that, well, you do one of two things. You say, oh, no, it doesn't correspond to the original assumptions, so it's a bad sample, and we'll look for a different sample system that does it, or else you say, gosh, maybe that's something else that we'd like to understand. Although, I must say that on many occasions we go for the first solution. Okay, when you've got a liquid crystal colloid, there are a whole load of length scales that are involved, and so just as when you're doing hydrodynamics. And so, for example, you've got a length scale that is, let's see whether, where is it there? So there's F, the suspension volume fraction, and so you've got a distance between the colloidal particles. You've got an electric field in there, perhaps, so you've got a relaxation length. You've got some kind of effective anchoring energy here that says to the director, I want to go in one direction and not another. You don't necessarily, but you might, and if you do, then you've got a characteristic length scale here that's sort of the so-called extrapolation length, and if zeta is small, then you've got weak anchoring, and if zeta is zeta is small, you've got weak anchoring, and if it's large, you've, let me see, if it's small, you've got strong anchoring, and if it's weak, you've got large we'll try again. Strong anchoring is W large, and zeta is small. Weak anchoring is W small, and zeta is large, and if zeta is larger than the size of the system in particular, then of course there are circumstances under which the size of the particles, there are circumstances under which we can ignore these things. Just to give you some. Okay. Here is a picture from Holger Stark's review article, just to show you, of about 15 years ago, which showed you the kind of structures that you can get around colloidal particles. And the reason and the result of that is that because the director is doing all sorts of peculiar things, the optical cross-section of the particle is much greater than its size. But I should say that often people want to put these things to make devices. And if they want to put things to make devices, they want the particles to be invisible. So this situation here is dead cute, but not of any interest to a device, at least not the classical device physicist. The classical device physicist wants to reduce his Friedrichs transition. He wants in particular to have a low magnetic Friedrichs transition so he can switch on very low power or switch with an accessible magnetic field. So these are really interesting things, but the whole point is that they are visible, whereas what you actually want is that you don't have any structure at all, at least you want if you are an engineer, and today I am being an engineer. Right, right. So those are interesting things. Here are some pictures. Often these particles stick together, and you can sometimes think of these particles as having an effective interaction between them. Right. So look at this picture here. You can kind of think of these particles as they're sitting in a bath, if you like. They're sitting in some kind of ordered bath, and there's an interaction, and the liquid the thermodynamics is governed partly by these curvatures and so on, partly by the thermodynamics of this thing here, and partly by the effective interaction. And that's very different from if I had just a mixture of two liquid crystals in which I could kind of suppose that everything was touching everything else, at least with the probabilities of the frequencies of them being there. So here are, when you get very close to some phase transitions, you get very subtle changes in the interaction, and you can, as a result, get dramatic flocculation when you by changing the temperature by marginal amounts. Okay, so the things that we've been interested in are magnetic liquid crystals. That's the idea. You put in a magnet, right? The magnet turns very rapidly, and it pulls the liquid crystal around with it. Here's a picture, and you can see here are my magnetic particles. Here is the pneumatic. In this particular case, the pneumatic wants to be at right angles. I put on a magnetic field, it turns the thing round, and as it does so, it pulls the pneumatic. Of course, the pneumatic might also want to turn, but the hope is that it will turn much more quickly. When I say the hope, and that's because it hasn't worked out the way that we would have hoped. Hasn't worked in the sense that my friends in Southampton do experiments and the effects are nothing like as dramatic. Okay, I'm almost at the end, actually, without having got onto the things that, right. So here are some stuff. Then the pneumatic isotropic phase transition decreases with temperature, usually because the isotropic is more the isotropic solution is more favored. But when it's ferromagnetic particles or ferroelectric particles, it can increase with temperature, right? So here are some predictions by my group actually, that Frederick's transition can reduce significantly, but the colloidal particles seem to clump or cluster, and there's evidence of some ferromagnetic and ferroelectric transitions, and these are things that we want to understand. I'm running out of time. Here are some pretty pictures by a group a group from Berkeley, and they're particularly pretty because nobody has ever in 30 years been able to reproduce them. Perhaps we should cut that bit from the too late. Here are all right, here's another. All right, so you see, what you do is you write off to the people who are making the colloidal particles, and the people who are making colloidal particles are actually making them to put in your body, because apparently you can steer drugs to some crucial, you're about to keel over, and then you can steer the particles to your heart, and lo and behold, you are woken up, and then they don't like your talk, and they turn you off again. So anyway, so here are the particles. Right, okay, and here are some experiments. What you can actually see is that there's a dramatic, so here's some dramatic, you put these magnetic particles in here, and lo and behold, at small fields, the particles turn very much more. I'm going to finish with some questions, and then I'm done. I was going to draw some things on the board, but here are the kind of here are the kind of things that we are asking. Right? What features in the particles are enabling the phase boundaries to either increase in temperature or decrease in temperature? Can I build a theory that is continuous between small particles and large particles? That's an important thing, because I want to change the volume of a particle while keeping the volume concentration fixed is something that I kind of want to do as a kind of theoretical, one of my first theoretical tasks. But somehow or other, if the particles are all small, then I can use some kind of effective sort of mean field, molecular field theory where everything is neighborly. But on the other hand, if the particles are sufficiently large, I look at it in a different way. I say, here is a sea of one set of particles. Here are my solution particles. They have an effective interaction between them. Actually, if I put the particles, if I'm going towards this phase transition, as soon as I have some particles in there, I'm going to have a miscibility gap. Usually we don't see this because the liquid crystals are anyway mixtures of a whole load of things. But here is this is something that I might be interested in. And actually, the particles are polydispersed. And the fact that I want to know how much the fact that they are polydispersed, because all of our baby theories suppose that the particles are monodispersed. So how can I take account of the fact that they are polydispersed, given that there are entropy terms that are associated with polydispersity? Okay, so here's this question about the frustration of the liquid crystal in the colloidal system, and how do I think about what the free energy will do? And here's Professor Katz's question repeated, right, which is that you're going to get charges in here, and you might get some stray charges, because it's very difficult when you put these things are dipoles, right? So if they are electric dipoles, what's the difference between it being an electric dipole and being simply a steric dipole? In other words, it looks like a cone or something, could be a steric dipole. Okay, so here's something else. They are very sensitive to external fields, and people work out the phase diagram of liquid crystals as a function of magnetic or electric field. In fact, Dr. Toe and I have just prepared such a paper. So how is this affected when we actually have its colloidal particles, its solution particles that are responding to the field? And so you might get something. In fact, you could even get phase separation that occurred in the field, but not without the field occurring. Right? Here's a chemist's kind of question, because actually the chemists, they can't figure it out. You go to your favorite salesman for ferroelectric particles. He gives you some barium titanate or some SMS or something, anyway, and then you put it in your favorite liquid crystal, and sometimes you get an effect and sometimes you don't, and again, it's not exactly clear what are the features that are going on. Okay, Right, here are some questions about ferromagnetism. My particles are ferromagnetic. Right, but even if my particles are ferromagnetic or ferroelectric, does this mean that the whole system will be ferroelectric? Does this mean that I can sort of order all of the particles in the whole system? Or do I actually need to turn it on with a very small field? So I have a very, rather than being true ferromagnetism or ferroelectricity, it's a very rapid turn on. And here's something else, right? The particles should form chains. Whenever you get charges in there, magnetic or electric dipoles, they should be forming chains. And our calculations suggest that the chains should be very long. So long, back of the envelope calculation, so long that they don't actually, that they don't fit into the system. But if that were the case, then you'd have a giant response, which is much larger than is observed. And I think, whoops, there are some more questions, but there's an etc. at the end, and I am over time, so I shall stop.
What? Solutions?
Solution's the word. Okay. I think we're out of time, Professor Ball. Somebody else, Professor Lewensky here, is itching.
Antonio.
Oh.
Thank you very much. Yeah.